Morning. I feel like there were a lot more people yesterday. Did we lose the rest of the after party? Was it that terrible? I don't know. Yeah, but you made it here. That's good. I'm glad to have you here. So the title says Java 24, better language APIs, and better language, better APIs, better runtime. But you know, Java 25 is coming out in September, and the feature set is already frozen. And I got content on 24 and 25 and 23 and 22, so we can really pick. But if it's okay with you, I want to focus on 25. Is that okay? I see some nods. Okay. Right, so as I said, then this slide is correct. This session will focus on 25. I cannot give you a full tutorial on all of these features, clearly, because that would take longer. So some of them I only touch briefly. We have videos on basically everything on the Java YouTube channel, so we can check those out there. And the slides are online as well. And if you have any questions, just raise your hand, and then I might not immediately see you, and then just yell. I'm not known for taking long pauses while I speak, so, don't wait for one. Just interrupt me. So Java 25 finalized a bunch of features, all of these. Not even all of these, like all of these and a few more. And we're going to go over a few of them later. But as I already said, there's more stuff in 24. And by the speed I'm going through these slides, you can tell I'm not expecting you to memorize all of this. Just to point out, a bunch of things are happening. 23 was rather minimal, but 22 also had a few things. And this is only finalized features. Then there is a bunch of stuff that is in preview or incubating or experimental. Then we have string templates here, which is neither anymore. It used to be a preview feature in 21, but I have an explanation for why it isn't any longer that we can get to if you want. What I would like to do is I would focus on 25 and then go through those features, and then we'll see how much time we have left. And then we can pick and choose what else you want to talk about. Okay, so I'll just get going. Let's talk about module imports. So I have a quick question. Which one do you prefer? Like the single type imports or the star imports? Who goes with option A? That's most of the people. I want to say like 80%. Who goes with option B? A few. Yeah, that usually happens. So there's also a few people going with that. So most of this segment will address those of you who prefer option B, but also the people like me, for example, will also find use for this feature. So star imports have a clear upside. They're more succinct, and they're just easier to manage manually, right? If you don't have an IDE at hand, they just make your life easier. The downside is it's less clear what you're working with. There is a chance of conflicts, but also it's just an arbitrary slice of an API. Some APIs are split across packages, and here you get like, I don't know, a half or a third of that API. I would like to present as basically an improvement over star imports, module imports. You go import module, and then you name a module, like Java XML or Java SQL at the top. And then imports the whole public API. And I'm going to discuss in a split second what that means. But very importantly, because many people just mentally shut down when they hear the word modules, your code does not have to be in a module for that, right? Like you can keep going with class path-based code. The dependency needs to be a module. That is primarily true for JDK modules, but of course this also works for your other dependencies if they happen to be in a module on the module path. Okay, so let's talk about what exactly is being imported here. It imports all public top-level types in all packages exported by that module. That is the most important part. And then the next two bullet points are only for module aficionados, because most of the rest will not really understand what I'm meaning here, but you can ask me later if you want to. But if you do know about qualified exports or about implied readability in modules, which requires transitive, and the other one is exports too, then those packages will also become visible. But the summary is everything that makes up the API of this module, you will be able to access. That is even more succinct than single type imports and more succinct than star imports because it imports a whole API. It's trivial to manage manually. And actually, I want to add a bullet point there. It's also really readable. If you see at the top of a class, import module Java SQL, you don't wonder what this is about. Clearly, it's dealing with SQL. And since it is short and not like a full block, you might actually read it. You might not just fold it and ignore it. Also in code reviews, by the way, you might actually be able to deal with it. Of course, it's less detailed than single type imports, and conflicts become even more likely. Like here, for example, I'm importing Java Base, Java Desktop, and Java SQL, and then I'm using a type called, wait, where's my cursor? There we go. called date, another one called list. But date exists in base and SQL, and list exists in base and desktop. People who use star imports are aware of this, and the solution is the same. You just have to manually import those types. There are actually very few conflicts like this in the JDK. So even though the JDK was not designed for that, it turns out that there's very few, like just the type name without the fully qualified part of it, that conflicts. So that's not a big concern within the JDK. So what are use cases? If you are using star imports, I want to posit that this is just clearly better. So, then this would be worth a look at. But also, and this is where people like me come back in, I write short little scripts to automate stuff on my system. I experiment a lot. I write a bunch of demos. In all of those situations, they're also really handy, right? Because it's like single type imports mainly shine when you have to maintain a larger code base. If you just write like 100 lines of code, you just put the import module at the top that you need and be done with it. I think that's really handy. We're going to skip that one. We're going to see it in a second again in the context of another feature. If you want to know more about this feature, JDK Enhancement Proposal 511 was the one that finalized this. And then, as I mentioned, we have the videos that dive deeper on almost all of these topics on our YouTube channel. They're all linked in the slides, and you'll see a link to the slides again later. I see more people trickling in, so maybe it was the party. Okay, let's change gears to something else. The simplified main method. And this is, yes, it's a feature, but it's also part of a larger feature arc that I want to discuss here. And that is about Java's overall state as an ecosystem, as a community. So Java is very mature. It has been here for 30 years this year. It has a very refined program model, meaning stuff like visibility, like the modules we just mentioned. It has a very detailed tool chain with first you run Java C, and then you run Java, and then you can pack it with a jar, and there's JPackage, and there's all kinds of tools. There's like 20 plus tools in the bin folder. It has a very rich ecosystem where whatever you want, starting from the JDK to your IDE, to your build tool, to testing frameworks, to web frameworks, to web servers, you have a bunch of choice, right? All of those things I just listed have at least 3 alternatives that are all good. Like in each of those fields, any of those 3 alternatives would be top-notch in most other ecosystems, right? So we have a richness to pick from. And that is great for us who professionally develop Java, but it's a hurdle for beginners. Because as a beginner, you don't need to read like 5 blog posts to discern which IDE is better for you. You just need an IDE. Just to give one example. So for beginner, this choice and this level of detail is actually more of a hindrance. But Java needs to stay approachable. Approachable for kids, maybe, if you want to, like, let's say your kid goes and starts hearing about what's called the Lego thing that you can program, other stuff that you start programming. Like, look, I know this other programming language. It's called Java. It works for Minecraft. Here, start with Eclipse or start with IntelliJ. That's not a great way to get a kid to be interested in this. Students still need to learn Java, so the next generation of educated software program developers does know Java. The front-end developer goes to the back-end, the MLAI folks who want to start running their stuff in production and maybe realize that Python isn't the best environment for that. All those people come into Java and they need an on-ramp. They need to have a way that takes them from I don't know Java, or maybe even I don't know programming, to I can participate in this ecosystem or in this community in a gentle slope instead of just a wall that they run into. So OpenJDK set out to start building that on-ramp. And I have 3 things here, 3 specific features that we're going to discuss. And then there's more that might come after this. So for example, I've been mentioning IDEs. None of this touches really on that specific topic. Okay, so let's go. Let's talk about these features. First of all, the main method is getting much, much simpler, and also the class around it. So the requirements for the string array, for main being static and public, and even for the class itself are all gone. You can now write in JDK 25, this is final, you can write this into a source file, and it would actually compile and run, yes? So this is not like a part of a source file, this is the full source file. Just write void main and then write your main method. And some of us are now rolling their eyes. It's like, why do I care? My main method just calls Spring Boot, and I'm done, right? True, but again, if you are a beginner or if you do experiments, if you do demos, this kind of stuff is really handy. Then another improvement is that finally we don't need to do system out print line and system out print anymore. We get a new class called IO that makes printing shorter, but also makes it really easy to read from the terminal. Have you ever tried that? Have you ever written Java code that just, maybe wrote a text adventure that reads the input? This is like 5 lines of just terrible code. Now you can just go with IO read line, please enter your name, and the user types the name, and there you go. Again, not very meaningful in large-scale applications, but really handy for just first experimentations. This is the slide I skipped in module imports, because the interesting thing about this is, so this is void main. This is just like my main method, and it uses lists and stream and big decimal and local date and random generator and all of that. And this is still the complete file, so there is no imports. And the reason for that is that a simple source file like this that does not contain a class definition gets an import module Java base for free. So everything that's in Java base, that's in the base module, you can just start using without imports, which again makes it easier to just get started. Okay, so let's say you've done all this, you've written your main file. How do you start now? What's the next step? The next step is just throw this file at the Java runtime. You can do this since Java 11 actually. So you don't need to first compile and then run it. You can just take a source file, throw it at the launcher, and it will do those steps in memory, right? It will run Java-C, which is a Java program, in memory, and instead of outputting it to the file system, it will just say, just put it in this memory file system, and then runs the bytecode from there. So it's actually, it's kind of simple as a feature because Java already has all the building blocks. What's new in a recent Java version, I think 22 added this, is you can expand this now and run simple projects that span more than one source file this way. So you have a main Java and a helper Java, and also got a jar from somewhere. And this is a little bit unclear, like how do I even get a dependency? Like, do you manually navigate Maven Central and download a jar? That's what you do with its dependencies. So where I get this jar from is a little bit murky, but let's say somebody gave you a dependency as a jar, then you could do this, right? You have your source code split into several files, and you can still just throw it at the Java launcher and launch it. Again, this is not meant for professional software development. This is meant for the early stages where you don't want to go through the process of, yeah, for that you unfortunately need a build tool. And then instead of somebody programming, they're now writing XML for Maven, which, maybe not the best beginner experience. I'm not harping on Maven here. Also wouldn't let them write a Bazel build file or a Gradle build file because that's just not what they're there for, right? They're there to learn code, to do something, not to manage dependencies and a build. And this gives us a really natural progression where we can start with a very simple main method. And if you need arguments to pass into your program, you can use the string array, you can add it. If you need to organize the code, you can have several methods in this simple source file. If you need a shared state, you can have fields even without the class definition still. You can explore JDK APIs, which come free thanks to the module import. You can explore simple libraries by just dumping them into a library folder somewhere. And you can split into multiple files. And what I didn't show here, you can also use visibility and packages there. So if this hobby project grows, and you still just want to use Java directly to launch it, you still can. You can still use packages, and then you have to use every segment of the package name has to become a folder, as we usually do anyways. So this is all pretty straightforward. And the best thing about it, you don't have to do it in this order. You can mostly pick and choose, which means that if you teach Java to somebody, you can give them a problem, and they can start solving it. And if they arrive at a point where they need to learn the next thing from this list, you can't just pick it. You don't have to be like, no, we have to do it in this specific order. No, if they never need arguments to pass in, you can take your time before explaining to them what string bracket args means. And that means that once they arrive at a problem, then you can show them the solution. You can show them the next step, which I think is the best way to teach and to learn. And for all of that, there's more sources over the JDK Enhanced proposals that introduce this, then some videos to follow up on. And I really think that this, together with something like records, with some improved APIs that happened elsewhere, are really starting to change how Java can or should be taught. I think the way of teaching Java together with object-oriented programming often means that students have the impression that Java is very complicated and indirect, which to a point is true about the language, or I would say was true since it is getting simpler, but it's also just a complexion of then also learning this new thing, this OOP thing that they never did before, right? Imagine somebody start a program with some Python scripts, and then you come along with, okay, let's do OOP in Java. They're learning two new things. One of them is just maybe not immediately obvious, while you need all of that indirection through OOP, and then that's often misattributed to Java. So I really hope that, specifically something like records, I would not teach first classes, then records. To a beginner, I'd be like, look, this is a record. It's a simple data holder. Then we can play with that a bit, and then maybe later be like, okay, if you need more freedom, maybe now is the time to introduce classes. So I think these features really open up a way to teach Java that really goes from the simple to the more complex, instead of overloading people with, okay, so before you start your first line, let's talk about what public means, and what static means, and what a class is, and what method invocation is, which is not necessary for somebody to just write hello world. Okay. That was my rant on teaching learning Java. That's something else. Let's talk about flexible constructor bodies. Also finalized in JDK 25. This concerns generally the topic of constructor chaining, or sometimes it's called telescoping constructors. If you have several constructors, then I would claim it is good practice to have one real constructor, like the good one, the one that assigns all the fields and makes sure that everything is in order, the one that does all the checks. And then ideally, all the other constructors just forward there. And the main reason to write it that way is that if you find a bug, for example, and realize, oh, we missed some validation, you only want to have one place where you have to update that validation, right? You don't want to have like 5 constructors that do some validation, and then, maybe the person updating, handling the bug only updates 3 of them. And then the bug still exists and comes back later, which is the most annoying part of the bug when you're like, hey, didn't we fix this last week? Right, so that's why I would claim that this is good practice, doing something like this, right? So I have this constructor here that assigns first and last strings and does all kinds of checks and whatever, and this other constructor that gets a middle name too doesn't repeat it. It just forwards to this one. That's what I mean by constructor chaining. With superclasses, this is enforced. Now I have a new class called 3-part name that extends name, and I have to call the superconstructor here. Like, I cannot just do everything down here. I have to call the constructor in the superclass. Without it, it wouldn't compile. But there are some limitations here. The idea is that if you have a class hierarchy, then you want the superclass to be initialized before the subclass runs any code. And that means, okay, then you shouldn't run any code before the supercall. So that used to be a rule in Java. You cannot have code before the supercall. And since if you have a chain of constructors in the same class, and then one of them eventually calls super, then if you could run code before this constructor call, then you would effectively still run code before the super constructor call, and that means the other rule is no code before before this. So in summary, up until Java 25, you could not run code before super and this. So as a consequence, or the consequence of that is this. That was intentional, right? If you have a class A that is extended by B that is extended by C, and you call new C, what will effectively happen is the code in the object constructor runs first, then A, then B, then C. Because the first statement in C is just super, and the first statement in B is also super. So you just immediately pass from C all the way up to object, and then the code is actually executed in a downwards fashion. And that is generally good, but it can have some downsides. So here I have this constructor of the name class, and in this case, it prints itself, which is not very common. But what I'm saying here, this instance, at the end of its construction, is exposing itself to the outside world. In this case, it's printing, but it could also be putting itself into a list maybe, or into a set, or registering itself with a cache, or whatever else, right? This is not common, and it's not really best practice, but sometimes it's necessary. And here I have the constructor of a subclass that extends it, that does the super call, and then at the end assigns the middle name. Right? This is what it has to look like before 25. But if you then create Jane, Jennifer, Doe, then this will print before this assignment happens, which is probably resulting, if this one overrides toString, in a null for the middle name. Which is weird, right? Wait, I created Jane, Jennifer, Doe, then why is the middle name null? And the reason is that this constructor exposed the instance to the outside world before it was really done constructing, which is not great. And it's also not great this being forced to not have statements before this and super if you want to check arguments, if you want to prepare them, if you want to split or share something. So for example, in this case, I have a first and a last name that I want to assign, again, in the name class. But I have an additional constructor that just gives me a full name. And the idea here is, well, I'm going to split it on the space, and then the first part is the first name, and the last part is the second name. And well, first of all, you can already tell, like, what if there's no space? What if there are several spaces? So clearly, I kind of actually want to apply some checks to this split. I want to do a little bit of work before, but I can't. So what I could do is just put the split here twice, and that also means the work of the split is done twice, which again, in this example, doesn't really matter. This is string operations really fast, but in general, it just doesn't feel good. And also there might be cases where this performance will really hurt. What I want to do is I want to make the split. I want to look at the result. I want to figure out where everything's okay and then pass it on to the next constructor, but I can't really. And then you can play around. There's other ways to get there. You can duplicate argument validation and field assignment across different invocations. You can add an internal constructor as an intermediate step to hack around this. Static factory methods are helpful. So there are workarounds for this, but it still means you might not be able to write the code that you really want to write. And records make this even worse because record constructors require chaining. This idea that there should be one canonical constructor that does all the important checks and is enforced by records. So that further limits the options that you have. And what we actually want to write is this. We do the split, and then we maybe do some checks and whatever, and then we call the constructor. That should be easy, right? And flexible constructor bodies in JDK 25 do allow that now. So conceptually, the constructor is now split into a prologue, the call to this or super, and then the epilogue. And the epilogue is just the normal constructor body, normal, as we know it today. The call to this or super is either explicitly or implicitly there, and the prologue is new. And in the prologue, you can do a bunch of things. Basically, you can imagine I'm working in a static context. I cannot touch the instance under construction except to assign fields. So if I have, again, this hierarchy of A, B, and C, and I call new C, what will happen now is I first run the prologue of C, then call super, then I run the prologue of B, and then of A, then comes the object constructor, and then I walk back down with the epilogues, right? So the part from object to epilogue ABC, that part is as before, but now I get code that basically runs up this hierarchy, and then we run it back down. So that's great. Now you can check arguments, prepare arguments, you can split or share arguments, you can also assign fields here. So now you would do it like this. Let's say you have a three-part name that extends the other name. And you get first, mid, and last. And now you can apply some checks early. You can, for example, in this case, I want to make sure that the first name is neither null nor empty. And then I will assign the middle name, and then I will call the super constructor. And if the super constructor does the stupid thing where it prints itself, it will now print itself correctly. That also means that this is awkward. This will look weird for us. This will mean that now subclasses should, by default, assign their fields before they call super. Because that way they can make sure that when any code in the superclass touches on the subclass again, then they will be in the correct state. And coming to this check, for example, for this preparation of arguments, we can do that as well. Here I'm just writing a little bit of code to put together another call. This is all very natural. Once you start using this, you'll wonder, like, why did I ever do it without? And the split also works reasonably well, or really well. You just do the split, and then call the constructors. So again, this limitation, no code before this or super, made sense, but with a little bit of leniency here, we can maintain all of its guarantees, but at the same time give us more freedom to design the code the way we want to. Then there's a surprise cameo by Project Valhalla here, and this is going to be, if you don't know what Project Valhalla is doing right now, then this might be a little bit confusing. In that case, ignore this slide. You can ask me later if you want to. But just for those who do know a little bit, Project Valhalla is considering null-restricted fields, meaning fields that cannot contain null. Like that kind of string, like maybe a string exclamation point, would be a string and not null. The way that it would work within the JVM is that no code is ever allowed to observe that a field is null, because a field needs to be null initially. Like when a new instance is created, it's nulls all the way. Like there's just no other way. So the idea is, well, okay, they can be null, but you can't see it. Never, ever. So that means that all fields that are non-null must be assigned before other code can see it. And this used to be a problem when considering how to implement, how to enforce this. And these constructor calls now make this possible, because that means that a subclass can be forced to assign all its non-null fields before handing control to another class that could potentially otherwise observe these fields being null. Okay, that was the Valhalla cameo. If you want more about this, JEP 513 introduced flexible constructor bodies. There's a video on that. And this is a talk by Brian Getz at JVMLS last year, where he goes also into the connection to flexible constructor bodies. So if that part was just a little bit too fast for you, go watch that video, and you'll get, well, not the current state of affairs in Valhalla, because it is almost a year old, but not that much changed since then. So you get an insight into what Valhalla looks like, and also what the connection to this feature is. Okay. 60% done with what we have to get to through today. Ahead of time compilation, or computation, I should say, not compilation. That was wrong. Ahead of time computation. Important difference. So Java has really good peak performance. Don't let anybody tell you otherwise. If you just look at CPU cycles, Java can definitely rival, specifically it's intended to written like that, definitely rival C and C++ code. But it might take a while to get there. Java has slow startup time and slow warm-up time. What's the difference between startup and warm-up? Those terms are not like, they're not like an industry standard definition there. But the way that OpenJDK uses those terms right now is startup is from you hitting enter on your command to launch Java all the way until it does the first meaningful unit of work. Meaningful unit of work means if you write a hello world program, then the first meaningful act of work is printing hello world, meaning the first thing in your main method. But if you're having, let's say, a Spring Boot app, then what you want to do is not launch Spring Boot. What you want to do is, probably reply to incoming requests. So all the Spring Boot initialization is still part of startup, because the first useful unit of work is you actually responding to a request that comes in. So that's startup. And then warm-up is from there to peak performance. And peak performance is also not clearly defined. There is no one point when the JVM says, okay, peak performance reached, I'm done now. So it's also a little bit vague. But that's the idea here. Those two terms mean from starting to you're doing something useful, to from doing something useful to you're doing it really fast. Those are two times that Java can take seconds, maybe even minutes to reach. And the reason for that is there's a lot of work being done at runtime early. We think of Java as a static language, but that's only because it's statically typed. In general, Java is a very dynamic language, and specifically a very dynamic runtime, where a lot of things are only decided really late and lazily. Class loading, call side linkage, constant pool resolution. First, the whole source code is only interpreted, and profiles are gathered, and then the JIT compiler realizes what makes sense to optimize, and then optimizes it based on those profiles. And if you don't know about all these steps in detail, that's perfectly fine. I'm also murky on the first couple. The point is, the reason why Java is slow in the beginning is not because it's lazy, but because it has to do a lot of stuff. And we would like to do that stuff ahead of time, ideally, right? In an ideal world, we just do all of that before we start the application. And then we can just start at peak performance. There you go. Wouldn't that be great? But as I just mentioned, Java is really dynamic. There's a lot of stuff that can change this consideration, like which classes are present on the class path, and maybe even agents or something that redefine the classes and the bytecode. How many implementations are there of an interface that determines linkage? Which classes with modules in the game, which classes can even see other classes? All of those things can only really be decided once the application is running. So how would you do that ahead of time? How would you decide at build time what any of those things are? And the answer is, ideally, you have a crystal ball. Ideally, you just predict the future. You just look at it and it's like, okay, I know what's gonna happen when we launch the application. Now, unfortunately, we don't have that technology. What we do have is training runs. So the idea is, well, we cannot predict the future, but we can do something that maybe looks like the future. So we do a training run, and then we can observe what's happening. We can gather all of the information there, and then we can make sure that when we launch the application for real, we build on the information we gathered in the training run. So that's what Project Leiden introduces. It's called an AOT cache, an ahead of time cache. And the general idea is what I just described. You observe the JVM, you capture all kinds of decisions in the AOT cache. And if you heard about class data sharing and the class data sharing archive, the CDS archive, then this seems familiar. It is an extension of that. And then this initial run that is used, or this training run is used as an initial state for a future run. I'm saying initial state because the JVM will still do its thing. It will still observe. So let's say during a training run, the method was optimized one way by the JIT compiler. Then at production, it might turn out, oh yeah, but that was because the training run that we had only used that method in a certain way. So what would then happen at runtime is it would do the regular thing where it de-optimizes and then re-optimizes. And that means it would take longer to reach peak performance. But importantly, this does not impact correctness, right? You will never be in a situation where because the training run is weird, then the production run will just forever be stuck in terrible performance, or worse, even make mistakes. It will still be correct and it will still reach peak performance. It just might take a little longer then. So it will fall back to live observations if that's necessary. I'm being very vague so far with what it actually does. I'm going to explain in a second what already happens ahead of time, but I still want to keep going a little bit with this idea here and explain how you'd actually use it. You don't need to memorize this by heart. I just want to show you that there's like a 3-step process. First comes the training run, which runs the application. What you can see here is class path app.jar. I'm running the app here, but I'm also running in this AOT mode record, where I'm creating a configuration. That's the training run. Then comes the assembly phase, where I take this profile and turn it into an AOT cache, and this does not run the application. It's just a thing that Java does on its own. And in the end, I would just launch the application in production as I would usually, and I would say, and here's the cache, please use that cache. So in general, we should have this 3-step process in mind, which is the training run, then the assembly phase, and then production runs. Many situations, this can be cut short. For, I would say, easy and medium complex cases, you can have a training run that immediately spits out the cache. You don't have to go through this intermediate step with the configuration for many cases. And then it becomes a 2-step process where the training run results in the cache, and then you take that cache for production. Okay, now we've talked through the concept and through how you'd use it. What does it actually do at the moment? Since JDK 24, what you get is class loading and linking ahead of time, which improves startup time by making the classes of an application instantly available in a loaded and linked state when the hotspot JVM starts. And as an example, benchmarks are always dangerous, right? This is not a promise to what will happen in your application, but just as an example, the Spring Pet Clinic started about 40% faster that way, and the AOT cache is about 130 megabytes, just so you get a little bit of an idea. So if those numbers are interesting to you, then you should explore it for your own application. If you think like, no, I don't care, either it's like 10x startup improvement or I don't go through the effort, then don't touch this. And then since JDK 25, we also get AOT method profiling to improve warm-up time by making method execution profiles from a previous run of application instantly available when the hotspot Java virtual machine starts. That means when the JVM starts, it already has information on which methods are called how often, and it can then already immediately decide what to optimize. So the JIT compiler can start working immediately. But what you could also think, like, wouldn't it also make sense to take the JIT compiled code and put that into the archive? And that's also being explored at the moment. That might be one of the next steps. So basically, when I went over the list of all the things the JVM does early, then now slowly steps of that are pulled into this ahead of time computation. And you will probably, at least for a while, have the same process of creating this cache, and you will just see more and more things being pulled in early. So meaning the cache size will slowly increase, and the performance improvements will slowly increase. And then at some point, there might be situations where, well, now we're going to double your cache for like 2% more. Maybe not everybody wants that. So sooner or later, I assume flags will show up for, yes, I want this optimization. I do not want that optimization. But for now, they're all kind of like low-hanging fruit, so to speak. So we're getting all of them. There are a few limitations. So if you create the cache and then you run it in production, then there needs to be consistency between those two runs. You need to have the same JDK release on the same hardware and operating system. The class path needs to be consistent, and I refer to the JEPs so they can read what that means. The module options need to be consistent, same thing. And JVM TI agents, which can redefine bytecode, can only be used sparingly. If these things are violated, the cache is just ignored. You just did the work with a training run for nothing, but again, it won't impact correctness. If you learn more about this, this is the JEPs that introduced these several features, and there's a short video that we made in October that has an outlook on this as well. Okay. A quick one on compact object headers, then we have a couple minutes left after that. Okay, wait, no, all that was my surprise deprecation, so we're gonna get there as well. So just a little bit of information here. We're switching gears again. Now we're inside the JVM. The runtime needs to track informations for each object. Like, what does the garbage collection do? Which type is this instance actually? Has it been locked on? All of this is happening under the hood and automatically. You don't really need to bother about it too much unless you want to. The point is, all of this stuff is stored in something that's called an object header. On 64-bit hardware, this is the most likely layout that you would have on JDK 24 and before, or even on 25 still, we're going to come to that. Which means, however large the data in the object is, on top of that come these 96 bits of extra information. And the dots are free, by the way, so there's a lot of free bits here. And this overhead, I mean, the JVM needs it. It's not like we can just throw it away, but from the view of the application, it's overhead. Like, the application doesn't want this. The application wants ints and strings, not object headers. The problem is that objects tend to be very small, and then the header becomes noticeable, right? If you have like an integer object, then the int is 64 bits and the header is 96 bits. That's ridiculous. That's more than the actual data. So on an average application, the header can be anywhere between 15 and 30% of the workload, of the memory consumption, is just headers. And ideally, we don't want to have those. The problem is that the subsystems I just mentioned, the type system, the garbage collection, the hashing and locking, all of these are very complicated and performance-sensitive systems that all collide in the header, right? These are very distinct things. Garbage collection and locking, you would think, don't have a connection really, but they do collide in this header. So it's not just like, oh yeah, we'll just change a few things around and I'm sure it'll be fine. Any change here will have large impacts. And so it's really a testament to how well the work was done within OpenJDK, led by Roman Kenke, by the way, who started when he was at Red Hat and who's now at Amazon. So this is one of the JDK enhancement proposals that was, to a large chunk, developed outside of Oracle, just to make obvious that OpenJDK is more than just Oracle. It achieved its first milestone, Project Lilliput, and boiled it down to 64 bits. And what those bits exactly are, again, you can study this if you want to. But they have several downstream effects. As I said, these different subsystems collide there, and these effects mean that in some special cases, the performance might actually be worse. And so that's why, at the moment, these object headers are not on by default. We'll get to that. But generally speaking, benchmarks are promising. We see, look, 22% less heap space, for example. Then the number of garbage collections is reduced. But you also get less CPU time, because if the memory is more dense, you get less cache misses, for example. If the memory is more dense, the garbage collectors do less work, which means the application can do more work in the same time. So it's primarily about memory, but as a secondary effect, you will probably see performance improvements as well. But as I said, those are not necessarily consistent. And so this is still being explored and tried out. So there is an additional flag that you have to use. Use compact object headers. And I invite all of you who are interested in your application's performance, if you have performance benchmark suites, run them with this flag and without this flag. Observe what's happening and go to the hotspot dev mailing list and report back and say, this is what I tried, this is the outcome, and then that will determine how this feature is being developed. Ideally, in the long run, this becomes the only option, like only compact object headers. But that depends on how this all pans out. If you have custom configuration of compressed class pointers or stack locking, And if you don't know what these are, then that's fine. But if you do know what these are and you have special configurations for them, be aware that only specific values work with compact object headers. There's more to learn about this. This is the JEP that made them final, but that JEP is very short. This is the JEP that introduced them experimentally in 24, and it contains all of the explanations and in way more detail, of course, than I just went through. And I made a video about this a couple years ago that you can check out too. Okay, unfortunately, now I do not have the time to tell you about all the things that are being taken away from you. And also, there's all of these features that we could go over. But as you can imagine, like, we don't have the time to do all of that in just 45 minutes. So if you have questions about any of these, I invite you to just find me and ask me. You can do that now. I'll be here until at least the middle of the day. And even if I'm just currently stuffing lunch into my face, ask me. I love to talk about all this stuff. Thank you for your attention, and I wish you a great rest of the conference. Where's the last slide? There we go. Thank you. I mentioned the Java YouTube channel a bunch of times. Go to youtube.com/Java. Also, if you're interested in the development of Java, check inside.java. And if you're interested in how to use all this stuff, check out dev.java. Those are all things that the Java developer relationships team at Oracle that I'm a member of maintains, and that give you a lot of good information. Have fun.